Hey everyone, in this video we're learning about extreme values. So our extremes are our maximums and our minimums, our high and lowest points on a graph. So we're looking at closed intervals, and we'll be starting with what are called an absolute maximum and an absolute minimum. And so the absolute maximum is the highest point on the graph. Every point on the graph is less than or equal to that point, and then the absolute min is every point on the graph is greater than or equal to that point. And so these are our extreme values of our function. Also, this is referred to as global maximum and minimum, or maxima and minima. So here's an example over here. We have two different graphs that we're going to look at. We'll start with cosine, the cosine graph, and we're looking again on closed intervals. So we're saying from negative pi over 2 to positive pi over 2. That's going to be our closed interval, our starting and stopping points. There is a highest point on the graph in between those two values. And we also have lowest points on the graph, and we have a low point in two different spots. It's the same y value or output value right here touching the x-axis. So that happens at negative pi over 2 and pi over 2. So now we'll take a look at another example. This is our sine graph, again on the closed interval. And notice the highest point on this blue graph occurs right here at pi over 2, and the lowest point occurs over here at negative pi over 2. So that's where our absolute max and min occur. Here are some more examples. So this is the same graph, or same function I should say, x squared. So y equals x squared. But we're considering different domains. So our domain, remember, is our input values. And so this first one, we're looking at negative infinity to infinity. So that's actually an open interval. There is an absolute minimum on this interval, and it's this lowest point right here at 0. And then this graph has no absolute maximums because the graph will continue to go up toward positive infinity. Now in this next one, it is a closed interval. It goes from 0 to 2, and so we have like a starting point and a stopping point, and those are actually going to be our absolute max and minimums. So we have absolute min at 0 and absolute max when x is 2. Now this one here, this is a half open, half closed interval. So the parentheses on the domain lets us know that at 0 it's open, and then you can see that with an open circle. So there's only an absolute max on that one, because we can't include 0 as the absolute min because that point is actually not on the graph. Now on this last one, there's neither a max or min because it's an open interval. And what would be the highest point is an open point, and what would be the lowest point is open. And so we actually cannot include those as our absolute max and min because technically those points aren't there because they're open. Alright, so now this leads us into what's next, which is our extreme value theorem. Basically what this theorem is talking about is that if we have our function that's continuous and it's on a closed interval, then it's going to have both an absolute max and an absolute minimum value. Okay, so we're going to take a look at some examples. And on each of these examples, we have a closed interval from A to B. And on this first one, we clearly see that there is an absolute maximum point and an absolute minimum point that's interior to the function. On this next one, we see again that we have an absolute highest or maximum point, and then continuous function, there is a lowest point. These ones happen to be at the endpoints. Now on this next one, absolute lowest point at one of the endpoints, and then we have absolute max in the interior of the interval. And then on our last one, we have absolute lowest point in the interior of the interval, and then the absolute maximum on the endpoint. So here I'm drawing a random function on a closed interval, and notice that we have more than one absolute max. In my example, there's 3 of them. They're all at the same y value or output value, and then there's one absolute min, and it happens to be at an endpoint. Now another example on a closed interval might be a constant function. Constant would just be a horizontal line, and you may wonder, does the extreme value theorem hold true for that? And it does, because every single point on that closed interval on that function can in fact be a maximum and a minimum, because if you look at this definition, as long as the points are less than or equal to the maximum value and greater than or equal to a minimum value. So the equal to part would be the key thing to consider on a constant functions graph, because the function value is equal to the maximum and the minimum at every point on that graph. Okay, so let's take a look at this one here. So this graph actually has a jump discontinuity. It is a function on a closed interval, a to b. Notice we do have absolute minimum values when x is 0 and x is 1. However, this graph is not continuous. It doesn't also have an absolute maximum value. If you look back at the theorem, That was a requirement. So we don't have an absolute max because what would be the absolute max is actually an open point. Alright, so now we're going to look at local maximum and local minimum values. So locally, another word is relative extreme values. So these points are relative to the points nearby it or in a neighborhood around it. So we're not looking at the entire graph necessarily, we're looking very closely like at a neighborhood around a point. And the way we figure out if it's a local max or min is if we look at open intervals around those points. So taking a look at this example here, here's a local maximum value. Notice it's not the highest point on the whole graph, but if I draw an open interval or neighborhood around that point, it is in fact the highest point in that nearby neighborhood. Very similarly to this local minimum value, it is the lowest point in the nearby neighborhood to the points relative to the points around it. Now this one here, visually we can see it's the highest point on the whole graph. It is in fact also a local maximum in addition to an absolute maximum. What about this point here on the endpoint? So on the endpoint, we can't actually draw an open interval around the entire point because there's nothing on the right of this endpoint to consider, so it's not an open interval. So it is in fact not a local extreme value. Over here on the other endpoint, we have an absolute minimum because remember when we learned about absolute max and mins, they could in fact be at the endpoints. But because the endpoints we can't draw an open interval around them, then we are not going to consider them local extreme values. Alright, we're ready to talk about the first derivative theorem for local extreme values. And we have that if the function has a local maximum or minimum, and these are going to be at interior points. Also, if the derivative is defined, then the derivative equals 0. Okay, so the derivative at that point is 0. So again, this is at interior points, and we already know that there's a local maximum in there. Then the theorem is saying that the derivative is 0. And think about why. So remember, the slope of the tangent line, or the instantaneous rate of change, is our derivative. So we're saying that that slope of the tangent line is 0. And that occurs when there's a max or min. So consider its maximum on this curve. Well, if you think about the tangent line to that point, the slope of that tangent line, because it's a horizontal line, would be 0. So anytime there's a max or minimum on an interior point, it would create a horizontal tangent line, so the slope would be 0, and the derivative gives us that slope, so we can say that their derivative is equal to 0. Okay, so now we're ready to talk about critical points. So critical points are going to be interior points of our function that have very specific qualities, but the whole point of this is to find absolute extreme values. So our goal is to find these absolute max and mins, and so what we need in that process is to identify a critical point, which occurs when the derivative is 0 or undefined. So anytime that happens, we call it a critical point. And again, these are the interior points to our function on our domain. So where can your function possibly have extreme values? It can have it at an interior point when the derivative is 0. Also, if the derivative is undefined. Lastly, at the endpoints. So the endpoints of the interval, we have to check those as well. Those are going to be for global or absolute extreme values, though not the local extreme values. So we'll check all three of these things, and that'll be our process for finding our absolute extreme values. So we'll find our critical points. That'll be our step 1. We will evaluate our function. So our function f, we're going to plug in our critical points and our endpoints. And then for the max and mins, we'll just look at the largest and the smallest of our values that we found. Let's take a look at this example. So we're going to be finding our absolute maximum and minimums of a function f of x equals x squared on a closed interval from -2 to 1. So we have this parabola function, and we're looking only specifically at a closed interval. So I'm going to add that into the graph. So we can see on the graph visually that the highest point occurs over here at -2, and the y value is 4. That's the absolute max. And then this graph has an absolute minimum right here at 0. So at x is 0, there's a minimum of y value of 0. So we can see what the results will be. There's absolute max and min, but let's go ahead and solve it algebraically. So we'll be finding our critical values by setting the derivative equal to 0, or looking when is the derivative undefined, because that was our definition for critical values. So first we have to find the first derivative. So the first derivative of x squared is just 2x. So we want to say, well, when is 2x either equal to 0 or undefined. So when x is 0, then the first derivative equals 0. And then if 2x was ever undefined, that would give us another critical value, but that's never true. So 2x will never be undefined on this interval. And recall, if a function is undefined, it happens when things like dividing by 0 occur, or taking a square root of a negative number. That would give us an undefined real number. That would give us imaginary numbers. So neither of those apply here, so we don't have an undefined situation. So we have one critical value when x is 0. Remember, we also are going to look at the endpoints on our closed interval. So we found our critical values. We're now going to look at our endpoints, and we have x equals -2 as our left endpoint and x equals +1 as our right endpoint. And then we have to evaluate our function at each of these values, so at the critical values and the endpoints. So we're going to plug in -2, 0, and 1 all into our original function, and we are looking for maximum and minimums. In other words, the largest and the smallest values that come out of our function. So when x is -2, we get 4. When x is 0, we get 0. And when x is 1, we get 1. And so our highest or largest value is 4, and our lowest is 0. So our absolute maximum occurs when x is -2, and the maximum value is 4. And our absolute minimum occurs when x is 0, and our minimum value is 0. Alright, let's take a look at one more example. Same concept, we're going to be finding our absolute max and mins. This time our function is x to the 2/3 power. So remember, when you have a rational exponent, you can rewrite it in radical form. So a 2/3 exponent means that it's actually a cubed root, and we are squaring x, or you can actually square the cubed root because of the numerator on the 2/3. Then our critical values, again, we set our derivative equal to 0 or c when it's undefined. So let's find our first derivative of this function, and I'm going to put it back in rational exponent form. It's easier to find the derivative using the power rule. So we'll bring down our 2/3 power and then subtract 1 from that exponent, and we'll get that the derivative is 2/3 times x to the -1/3. We can rewrite that with a positive exponent if we put x in the denominator, and we can even put it back in radical form for the purposes of evaluating our function in just a moment. So that's going to be our first derivative, and we want to set that equal to 0 to find our critical values. So we're saying, when does this function equal 0? And it actually will never equal 0, because there's no value we can plug in here to get this function to equal 0. Now, when is this derivative ever undefined? Well, notice, if you actually plug 0 in for x, then you would be dividing by 0. So this one is undefined when x equals to 0. Okay, because it would be like 2 divided by 0. So we don't have the first derivative ever equal to 0. That didn't give us any critical values, but we do have that the first derivative is undefined if x equals to 0. So we have a critical value when x is 0. Then we're going to look at our endpoints. So when x is -2 and when x is 3. Last, we'll evaluate our function at these 3 x values and looking for the highest and lowest values, giving us our max and min. Okay, so remember, we are plugging back into the original function f, not f prime, not the derivative. So f of x was equal to x to the 2/3, or in radical form, cubed root of x squared. So plugging in -2, we get cubed root of 4. Plugging in 0, we get 0, and plugging in 3, we get cubed root of 9. So cubed root of 4 is approximately 1.6, and cubed root of 9 is approximately 2.1. So we have a lowest point, a lowest value. Our lowest output is 0. That happens to occur when x is equal to 0. So there's our absolute minimum. And we have a highest point, our 2.1, and that one happens when x is 3. So we have our absolute max when x is 3 and our absolute min when x is 0. And now we can verify this with the graph. So this is the graph of our function on that closed interval. At -2, we do not have a highest or lowest point, but at 3, we do have the highest point on the entire graph. And then at 0, we have the lowest point on the entire graph. Alright, so we were learning about max and minimum values, absolute and local, and we will explore this further and learn how to use the derivative to find local extreme values. Thanks for watching. See you in the next one.